to spend a little bit of time talking about some research that I did about how we understand the universe. We now know that it's all right. Is that better? All right. Let's see if that works. All right. Good. So I'm going to be talking to you about 3 decades that really changed our perspective on how we view the universe. When you go back in history and look at the first recorded measurements of the night sky, it goes back to 1000 BCE, to the Mesopotamians. They were the first to actually measure the position of stars in the sky. But of course they had really no idea what the scope and size of the universe was. And for about 2,000 years, we thought that the Earth was the center of everything. And we'll go into a little bit of the history of that. But only the last 100 years have we really gotten to appreciate the size and scope and the vastness of the universe. And my computer is stuck. Okay, hang on a minute. What else did I do?
Kyle getting beamed up in the phone shelf. Okay, that's pretty cool.
What is going on here? There we go. Okay, sorry about that. So, we now know that the universe is about 100,000 light years across, and it's about 30,000 light years at its center, okay? And it's a spiral. One light year is about 6 trillion miles, so it's something that's totally incomprehensible in terms of distance. And we also know that the sun is not at the center of the Milky Way. The sun sits about 28,000 light years from the galactic center. We, of course, know that the Milky Way is one of many, many galaxies in the universe. A conservative estimate says that there may be 200 billion galaxies, and the upper limit that I've heard is over 1 trillion different galaxies in the universe. And that we also know that the galaxies are moving away from each other. And because of a scientist named Albert Einstein, we know that gravity has a totally different form than what we thought of years ago with Isaac Newton. And Einstein said that gravity is actually the warping of space-time, which causes things like the bending of light and the formation of very odd structures like black holes. All this knowledge has only been acquired in the last 100 years. And in fact, I was explaining to someone earlier that January 1st, 2025 will be the 100th anniversary of Edwin Hubble's first paper in which he describes the fact that Andromeda is outside the Milky Way. And that is a significant milestone in the history of astronomy and astrophysics. And it turns out that those 3 decades, between 1900 and 1930, were absolutely critical to our understanding of the universe as it is today. And that's what I want to cover today. But we're going to go back in time a little bit. And you know, this period between 1900 and 1930 really was the birth of a couple of new sciences. One is experimental astrophysics. This is where we apply new tools and techniques to really reveal the structure of stars and planets and galaxies. And we'll show you how that happens, or how that has happened. And the other is cosmology, which is trying to understand the origin, development, and structure and history of the universe. Now, I'm not a cosmologist. I cannot speak with any authority on cosmology, and I can speak with marginal authority on experimental astrophysics, so I'm not going to talk about cosmology today. And if you have any cosmology questions, I will refer you to the solar system ambassadors in the audience, right? But let's talk about what we're going to talk about today. First, I'd like to give you a review of our understanding, mankind's understanding of the universe up to the 17th century. And it went through a lot of changes. There was a great period of stasis where we had one picture of the universe and that's the way it was. And then we started making measurements and doing mathematical modeling to change that view. And then in the 18th century, an astronomer discovered something in his telescope which he could not understand, which he called a nebula. Right? And these were curious stellar objects, and we'll talk about nebula because they play a very critical role in the development of our understanding of the position of the universe. In the 19th century, science really started to take off, and there were many scientific and technological breakthroughs that actually contributed to the improvement of our ability to measure things in space. And we'll review several of those most important ones. And finally, we'll walk through the big leaps that took place between 1900 and 1930, which actually led to our understanding of the universe today. So we go back to the beginning. We go back to a period of geocentrism, where the Earth is in the center of the known universe. And of course, the main proponent of that is Aristotle. Aristotle's view was that in space, planets and stars were perfect spheres, and they moved in perfectly circular orbits. And those orbits were like nested orbits, one within another, each planet within a crystalline sphere that would rotate around the Earth. At the very outermost sphere is the sphere of the stars. And they differentiated between stars and planets because stars move in unison across the sky, whereas planets move independent of the stars. And at the very outer sphere, Aristotle pointed out or proposed that there was what he called a prime mover. The Greeks believed in a very cause-effect relationship around the universe. And Aristotle questioned, well, if things happen by cause and effect, what is the first cause? And Aristotle ascribed that to the prime mover. And this will become important later. There was an issue with Aristotle's model. And that is, if you watch planets move across the sky, at some points, they trace a curved motion. And here's a picture of Mars as it moves across the sky over several days. And you can see that it moves back on itself and then moves forward. And Aristotle's model could not explain that. Well, enter Claudius Ptolemy. He lived in Alexandria in Egypt. And he proposed a modification of Aristotle's model. Rather than the planets moving in a circle around the Earth, the planets actually moved in a circle that itself was moving around the Earth. And he called this, the planet orbit, the epicycle, and the epicycle would move around the planet Earth. So the motion of the planet is described by the red line on this chart. And that would explain the fact that planets seem to go backwards at certain periods of its cycle. This was a successful model in terms of predicting many of the aspects of planetary motion. But it wasn't perfect. But it was one that held sway until 1543, so almost 2,000 years of history where we had the Earth at the center. And Ptolemy, which lived around 150 AD, proposed his model of the universe. So almost 2,000 years, we had the Earth at the center of everything. Now, the church believed strongly in this model of the universe, right? And they found biblical support for Earth being in the center of the known universe. And we'll come back to that because that plays an important role a little bit later. But then a Polish astronomer and actually a mathematician, his full-time job or his day job was as a canon in the Catholic Church, and canons were administrators of the Catholic Church. But he was a very fine mathematician. And he was troubled by the fact that Ptolemy's model was not as good as it could be. So he tried as much as he could to try to figure out what was wrong with it. And he ultimately realized that, the Earth being at the center is not the way to look at it. And if you put the sun in the center, the mathematics become a lot easier to describe the motion of the stars and planets. And so he proposed a model where the Earth is in the center. Now, he became very famous for his mathematics, but he was very leery about proposing this in a written form because of concerns about how it might be viewed by the church. And just near his death, a few years before his death, he put together, with the help of an aide, his book, and it got published in 1543. And he was given a copy of this book on his deathbed. And the book was called On the Revolution of Heavenly Spheres. And in this book, he describes his model where the Earth is at the center and the Earth moves. The Earth actually spins on its own axis. This was a revolutionary idea that was first in print by Copernicus, although others had been talking about this for some time. Now, Copernicus dies. People are looking at the model. Now they have two models of the universe. Which one is correct? You've got Ptolemy's model on one side, you've got Copernicus's model on the other side. A scientist named Tycho Brahe from Denmark decides that, the problem with these two models is the data is not good enough to distinguish between the two models, and if we had good enough data, we could determine which model is correct. Now, to the credit of the Catholic Church was not against the Copernican model initially. It actually proposed that other ideas besides the Earth-centered model could be discussed as long as you did not say that that's how it actually was. You could use it as a mathematical model, but that's about it. So Brahe decides that he's going to make the most accurate measurements of the night sky possible. And with the help of the King of Denmark, who gave him an island to build an observatory, he builds an observatory. And at that observatory, he builds large astronomical instruments, because the larger the instrument you have, the more accurately you can measure the position of the stars and the planets. And Brahe's idea was he was going to collect as much data as possible, and he himself was going to solve this problem of the Copernican model versus the Ptolemaic model. The problem was that Brahe was an excellent experimentalist, but not that great a mathematician. And he hoarded the data. He would not let other people see it. Near the end of his life, he hired a young German mathematician named Johannes Kepler. And he invited Kepler to come to Prague, where he had since moved, to help him study and analyze data that he had collected over the 20 plus years that he'd been studying the sky. And a year after Kepler joins Brahe, Brahe dies. And on his deathbed, Brahe says to Kepler, "I have promised the king to publish my data. Please compile all the data and get it published." Well, this is a boon. This is a boon for Kepler, because he now has 20 plus years of very good data to analyze. And he is a consummate mathematician. So he spends years reviewing this data and trying to understand and make sense of the Copernican model and the Ptolemaic model. And he realizes that if you made a slight correction to the Copernican model, everything falls into place. The mathematics allow you to calculate the position of the stars very, very accurately. And that correction is introducing an elliptical orbit of the planets around the sun. So he proposes an elliptical orbit. He also proposes that the planets are not moving at constant speed, which is also contrary to the Aristotelian model, which says that the things in space are perfect, and therefore, why should they change? This is a mathematical model, but there was no physical basis for understanding why this worked, although it worked very, very well. We needed some more data. One of the other things that Kepler did was he also studied optics. During that 8-year period where he was compiling Brahe's data and trying to analyze it, he also studied optics. And he wrote a very important book, which is actually still used today as an introduction to optics. And he also developed the inverse square law for brightness. Basically, if you're a person standing at a distance d from a light pole, and you measure the brightness of that light pole, if another person is standing a distance 2d, twice the distance from that light pole, the brightness goes down to 1/4. This inverse square law was written for the first time by Kepler, and this becomes important later on in our story. Well, now we have to see what other data we can collect, right? And of course, we know the story of Galileo. We had Galileo's exhibit a few years ago. We associate him with using a telescope to look at the stars, but the fact is that Galileo did not invent the telescope. The invention of the telescope was in Holland by a man named Hans Lippershey in the early 1600s. He was an optician, and he discovered that if you put two lenses together in the right configuration, you can increase the magnification a factor of 2 or 3 times. And this became very commercially important and militarily important. And he tries to get a patent on this idea of a telescope, but the patent office says, no, you can't have a patent on it. And his idea is used by the military, and it's used by the maritime industry. Nobody had thought of pointing it to the sky until Galileo showed up. And Galileo made improvements on Lippershey's telescope, improving the magnification to about 20 times, rather than the 2 or 3 times that Lippershey had developed. And Galileo was the first to point the telescope in the night sky. Now, there's some discussion as to whether someone in England might have done it before him, but for the purposes of discussion, let's just say it was Galileo. Well, he makes some astounding discoveries. In 1609, he discovers that the surface of the moon is not smooth. It's not what Galileo said. It's rough, it's got mountains, it's got pits on it. He observes planets around Jupiter. He observes the rings of Saturn. So these objects that we thought were perfect spheres up in the sky have structure to them. And the real clinching piece of data is that in 1610, Galileo observes the phases of Venus using his telescope. And if you do the mathematics, the phases of Venus by the Copernican model would be different than the phases of Venus by the Ptolemaic model. And it turns out that what Galileo saw confirmed the Copernican model of the motion of the stars. So Galileo, of course, being a person who relies solely on his observations, decides that this must be the way that the universe works. But the Catholic Church is getting a little bit antsy now, okay? And so they form an inquisitorial commission to look into this question of heliocentrism versus geocentrism, and they formally deem Copernicus' book to be heretical and add it to the index of prohibited books. But Galileo was not going to be deterred. The Inquisition had Galileo swear an oath that he would not propose the Copernican model as being true. He could discuss it, but he could not propose that the Copernican model be true. But he was not going to be deterred. So rather than openly saying that the Copernican model is true, he writes another book. He writes a book called The Dialogue Concerning Two Chief World Systems. And it's basically a dialogue between two groups, moderated by a third individual, and one person supports the Aristotelian model, or the Ptolemaic model, and the other supports the Copernican model. And the person supporting the Aristotelian model, he called Simplicio. And the Pope reads this book, and he says, wait a minute, you're talking about me. And so Galileo is brought in front of the Inquisition. And he is found to be vehemently suspect of heresy. Now, there are different grades of heresy, okay, and he's found to be vehemently suspect of heresy. Good thing for Galileo, because if he was formally convicted of heresy, the punishment would be death. But the Pope said, all right, Galileo, you're a famous man, you've only been vehemently suspected of heresy, and so he sentenced Galileo to house arrest. And the Pope put Galileo's book on the index of prohibited books. It was not removed from that index until the late 1700s, and the Church did not apologize for treating Galileo so badly until 1990, or early 1990s. They finally came around and accepted the fact that the Earth is not at the center. But we're not done, because there was still an open question. Okay, the sun is in the center, the planets move elliptically, Galileo's data confirms the Copernican model, but nobody understood why it should behave that way. There was no physics undergirding the mathematics that Copernicus and Kepler had developed. Right? And it was Isaac Newton who actually developed the theory of gravity that would explain the orbital motion of the planets. And using his theory, he calculated what an orbiting object, what its speed would be. And he estimated the speed of an orbiting object around Earth to be about 18,000 miles per hour, which is pretty darn good when you think that he was doing this calculation in 1680. Before there were any rockets, any missiles, he was calculating the speed of an orbiting object. He goes on to develop a new branch of mathematics, which we call today calculus, but it was co-developed by a man named Gottfried Leibniz. And in fact, the word calculus is the word that Leibniz used, even though we associate calculus with Newton. And he wasn't going to be stopped there. He looked at light from the sun, passed it through a prism, and was the first to observe the physical spectrum of light. And he continued to develop a new design for telescope. And this design becomes critical later on. It is a reflecting telescope. Galileo's telescope was a refracting telescope, one lens in front of another. Newton's telescope is a reflecting telescope, where you have an object out here. The light shines through the scope, hits a mirror, reflects, hits another mirror, and then the observer can see the image. During Newton's time, mirrors were made out of an alloy of tin and copper. It reflected about 50 to 60% of the light that hit it. It was susceptible to oxidation, but it was a significant improvement over the ability to see objects in the night sky with a much shorter telescope. And this becomes important later on, so keep that in mind. So let's skip ahead to the 1700s. People are building reflecting telescopes, refracting telescopes. The telescopes are getting bigger and bigger and bigger. The idea being the more light you capture, the better you can see things. And the next person in our story is a man named William Herschel. Herschel was a musician. He was a musician who turned astronomer. He was part of the German military, and as a musician in the military is a great gig, because basically what you wrote is marching anthems and songs for the military. You conducted the military band, and everything was hunky-dory until the Germans went to war, and they said, all right, all you musicians, get out in the front line. And William said, you know what, that's probably out of my wheelhouse. He flees to England. But he still has this passion for astronomy. So he gets a job, being a music teacher and conducting symphonies, but in his background he starts building telescopes. So he builds a 20-inch refracting telescope. So 20 inches means the diameter of the objective lens. So a 20-inch lens on the front of this telescope. And then he switches to a reflecting telescope. And he builds a reflecting telescope that has a diameter, a mirror diameter of 48 inches. It was the largest reflecting telescope of its kind in the time. But he's still using the material, the tin copper alloy that Newton was using, which only reflects about 50 to 60% of the light. It oxidizes over time. So he actually built two big mirrors, and every 3 months he'd trade the mirrors out and repolish the one that he took out. A lot of work. This is a diagram of what that telescope looked like, and Herschel would stand on this platform and look through the lens and call down to his sister Caroline, who'd be on the ground, and he'd be describing what he is seeing. Remember, this is before photography. So he's making these observations, and he makes some pretty significant observations. He's the first to discover the planet Uranus. He discovers 2 moons of Saturn, Enceladus and Mimas. Am I pronouncing that right now? But his probably one of the most significant discoveries for the purposes of this talk is he discovers these things called nebulae. And a nebulae is basically a cloud. Okay? It has really no form or structure, but you know that it's there. And nebula is the Latin for the word cloud. But nobody knows what these nebula are. But he sees them all over the place. He discovers 2,400 of these in the night sky that he's looking. That becomes a critical part of this story. In 1785, he makes the first map of the Milky Way, and here's what his map looks like. The sun is right there. Now, remember, at this time, we had no way of measuring distance from one stellar object to another. He makes some assumptions. He says all the objects have the same absolute brightness, and he says, okay, the sun is going to be at the center of the Milky Way, and this is what the star field looks like in the Milky Way. 1785. But you know, this question of nebulae really continued to be a nagging problem. The next person in our story is a man named William Parsons. Parsons lived in Ireland. His father was an earl in the Irish nobility. He was the Earl of Ross in King County, Ireland. William studied mathematics in Dublin, and he was also an amateur astronomer and built telescopes with the goal of understanding nebula. And he built the next big telescope. In 1841, his father passes away. He moves to his home county in Ireland, and in a castle called Burr Castle, he builds the largest reflecting telescope of its time. It is called a Leviathan. It's got a reflecting mirror 72 inches in diameter. It's 57.5 feet tall, and Parsons would stand right here, look through the telescope, and draw the night sky. And he makes one of the first really accurate pictures of a nebula. And here's what he observes. This is a reproduction of his drawing of the Whirlpool Nebula. And he notices something very curious. It's got some structure to it. It looks spiral. It's got arms coming off the side. And to tell you how impressive this drawing is, here's a photograph from the Hubble Space Telescope of the same nebula. And to me, it's remarkable how accurate William Parsons' drawing of the Whirlpool Nebula was. Now, some people have argued that Parsons' drawing is an inspiration to Vincent van Gogh's Starry Night. I don't know whether this is true. I leave it to your own imagination, and you can compare the two pictures. But now we've got nebula that have structure to them. Why? Nobody really understands. Now we're going to go into the next century, or later into the 1800s, to talk about the tools that were being developed that will really play an important part in this story. So, in the mid-1800s, a man named John Draper, who was a doctor and a chemist and a philosopher, he studied in England. He came to the United States, lived in Virginia for some time, and then moved to New York. And he becomes the founder of the Medical School of New York. But he's a chemist as well, and there was a brand new technology. There was a brand new technology that was just coming to fore, and it was photography. And William Draper develops a method to improve the photographs from the daguerreotype method. And he becomes the first man to actually take a photograph of a heavenly object. And here's a photograph of the moon that Draper himself took. Okay? He put a camera on the end of a telescope and took a photograph of the moon. This was a technological marvel for the obvious reasons, but a particular marvel for astronomy. Because prior to this, you had to rely on somebody's notebook and a written account of what they saw. Now, you could take a photograph and actually show them what they saw, what you saw, and have them compare to what they saw in their telescopes. The next great improvement was by two German scientists, Robert Bunsen and Gustav Kirchhoff. So you probably know Bunsen if you ever worked in a chemistry lab in high school. You have these little burners. The Bunsen burner is named after Bunsen. And if you've ever studied electricity, you know about Kirchhoff's rules. Right? They were at the University of Heidelberg. And they were looking at taking elements, heating them up in a flame, passing the light through a prism, and then looking at the spectrum that was coming out. And they found something very curious. What they found is if you just had a continuous spectrum of light from a light source, you get the regular spectrum. But if the light is being emitted from a pure chemical element, a lot of the light is missing. There's only emission from certain lines. Okay? You only get certain lines on the spectrum. And if you take that same continuous spectrum and pass it through a gaseous form of whatever element you're looking at, you get this absorption spectra where the lines are, where the continuous spectra is there, but you get dark bands in the continuous spectra because of absorption. Well, it turns out that when they were doing their studies, whatever element, each element has a different spectra. So, hydrogen, helium, lithium, if you go down the periodic table, each one of them has its own characteristic spectrum. This is important because we're getting light from stars. What if you could put that light through a diffraction grating or a prism and actually determine the composition of stars or light coming off of planets? And the first person to do that was an astronomer named William Huggins. Okay? Here's what it would look like. You have a hot star that in and of itself, if you pass the light through a telescope and pass it through a diffraction grating or a prism, you get a continuous spectrum. If the light passes through a gas nebula and some of the light is absorbed, you get this absorption spectrum where you get dark bands. Or if the gas absorbs the light and re-emits it, you get this emission spectrum. So by looking at the spectrum coming off of these stellar objects, you can get an idea of the composition. So now, we're not just looking at a dot of light, we're looking at what that light can tell us about the composition. And Huggins was the first person to actually make a measurement of spectra. He wasn't sure what the element was. Eventually it was found out that it was oxygen. But he's the first person to make a spectra of a stellar object. And this becomes a critical element in the story moving forward. And finally, in that period, there was a Frenchman named Jean-Bernard Léon Foucault. Okay? He wanted to study medicine. Unfortunately, he had a bit of a condition, hemophobia. He had a fear of blood. So after being in medical school for a short period of time, he changed careers to become a physicist. And he made some very important contributions to physics and astronomy. He developed a pendulum experiment, which is the first time anybody had actually proved that the Earth rotates on its own axis. Remember, Copernicus had talked about it in 1543. About 300 years later, Foucault actually gets the experimental evidence to prove that the Earth, in fact, is spinning on its own axis. But his most important contribution, physics, for my discussion, is that he applied a new chemical technique where you can deposit a very thin film of silver on a plate of glass. This technology was developed by another, a German scientist named Liebig. He was looking at depositing silver to make just mirrors for commercial applications. And Foucault was the first one to actually deposit silver on a curved surface with the idea of being able to use it in a reflecting telescope. Now, what's the advantage of silver? I mentioned that the copper tin alloys that were used at the time only reflected 50 to 60% of the light. If you have a silver mirror, you can capture 90+% of the light hitting the mirror, right? Which means you're going to significantly improve the light capture and the image quality from the telescope. So, in the 1800s, we've got the beginnings of astrophotography with Draper. We've got better mirrors by Foucault, and we've got the ability to analyze the light coming from stellar objects using spectroscopy and determining their chemical composition. Now let's put all of this stuff together and see where it goes. One of the things that was changing in the turn of the previous century was the epicenter for astronomy was moving from Europe to the United States. Part of the reason for that is that wealthy patrons would endow money to build observatories on top of mountains because they realized that the normal observatories that are in cities are becoming more and more polluted because of the Industrial Revolution is taking place, that it was much harder to take images. So let's put a telescope on a mountain. So that's why the Lick Observatory outside of San Jose was built. That's why the Mount Wilson Observatory outside of Pasadena was built. That's why the Lowell Observatory in Flagstaff was built. And Harvard College built an observatory in Peru to look at the southern sky on top of a mountain in Peru called Boynton Station. All of these observatories will play an important role in the story moving forward. Now, in the late 1800s, there was an astronomer named James Edward Keeler. He's one of a group of astronomers that come out of the Midwest. He was born in LaSalle, Indiana in 1857. His interest in astronomy was kindled by observing a solar eclipse when he was 12. He decides to go and study physics at Johns Hopkins University. And a really pivotal element in his career is that he joined, in 1881, he joined a mission led by Samuel Langley, the same Samuel Langley who goes on to become the president of the Smithsonian Institution, to look at solar radiation from Mount Wilson. And he becomes an assistant to Langley at the Allegheny Observatory, where Langley was at the time. After that short stint, he goes to the University of Heidelberg. He probably listened to lectures by Bunsen and becomes an expert in spectroscopy. He then moves to the Lick Observatory near San Jose, and in 1888, he discovers that Saturn's rings have a gap in them. It's the first time anybody has observed that. And because he was well-versed in spectroscopy from his work at Heidelberg, he starts taking a look at the light coming off the rings of Saturn. And he observes a spectrum, of course, but the lines are not where they're supposed to be. They're actually shifted toward the red end of the spectrum. And he's trying to understand why that should be. They're relative to each other in the right position, but they're moved toward the red. And he realizes that this is due to rotation or movement of the object relative to the observer. And so he measures the rotational rate of Saturn's rings at the center, near the center of the rings and near the outside of the rings. And what he finds is that the rotational rate of the ring is faster near the center than it is at the outside, which is totally the opposite of what you would expect if the ring was one solid piece. So he discovers that Saturn's rings are made of particles and not one solid piece, which was what was hypothesized before. But he didn't stop there. He went back to Allegheny because he fell in love with the daughter of the director of the observatory at the Lick Observatory, and knew that as an assistant to the at that observatory, he didn't have enough money to take care of this woman. So he takes a directorship at Allegheny for a couple of years, and then goes back as the director at the Lick Observatory in 1898. And there they have a telescope that nobody's been able to fix. It's a 36-inch reflecting telescope with a silver mirror. And if somebody could fix it, they would be able to get tremendous images from it. And Keeler is the one that figures out how to make this telescope work. And he discovers something astounding. He discovers that the universe is awash in nebula. In fact, he estimates there are 120,000 nebula in the visible night sky. Okay? And the arrows are pointing to what these nebula look like. And this is an image from the cross-link telescope that Keeler had used. So the question of nebula comes back again. There are more and more of them, but we still don't know what the heck they are. So the big question, what are they? Are they just regions of gas? Well, unlikely, because remember, Parsons had shown that they have some structure. Okay? There was a prevailing hypothesis that maybe these nebula are actually what are called island universes. Okay? Basically, what we would refer to today as a galaxy. But nobody had really any idea whether that was true or not. And where are they in the night sky? At this point, we had no real way of measuring the distance between stellar objects. Well, now we get into the early part of the 1900s, right? The most significant period in history. And there's an astronomer named Vesto Slipher. And Slipher was born in Indiana, another Midwesterner. He receives a bachelor's, MS, and PhD in mechanics and astronomy from the University of Indiana. He moves to Flagstaff, Arizona to work at the Lowell Observatory. And Slipher is a spectroscopist. And so he starts taking spectra of planets, stars, and nebula. And just imagine this, right? You have a very small amount of light coming from an interstellar object. You have to take that light, you have to put it through a prism or a diffraction grating to make a spectrum. And so the amount of light in each individual line on that spectrum is very, very small. Now, if you've got a camera on it, you can do very long exposures, and that's what Slipher did. He had to take exposures over several days in order to get spectra of nebula because they were so far away. And some of these spectra took 40 hours of telescope time to generate over multiple days. And he observes, like Keeler before him, he observes a shift in the spectrum. Okay? And that shift was specific to the Andromeda Nebula. And he says, wait a minute, if I do a calculation assuming a Doppler effect, the Andromeda is moving toward the Milky Way at about 300 kilometers a second. And that didn't make any sense. So he continues to measure the spectra of nebula. He measures 15 nebula. Most of them are moving away. Andromeda is moving towards the Milky Way. And he delivers a paper at the American Astronomical Society, and this is one of the few papers in the history of the society where at the end, the author gets a standing ovation. Because the amount of work that Slipher had to do to measure the spectra of these nebulae was astounding. And remember, he's doing it over successive days, so he has to set up his telescope in the right position every day and get the same light from the same object. And so he receives a standing ovation. Well, who's in the audience in the front row? A man named Edwin Hubble, who turns up later in our story. Slipher goes on to measure 25 additional nebula. Sees 22 of them are speeding away. But you know, the problem is we still don't know where they are relative to the Milky Way. They're moving, but in which direction are they moving? And where are they in the night sky? The problem turns out to be a problem of actually measuring distance. Okay? Now, up to this point, the only way to measure distance was a technique called stellar parallax. And this was, invented by the Greeks. Okay, parallax was used by the Greeks. Basically, the technique is to measure the position of an object of interest at two different times in the Earth's orbit around the sun. And if you measure this angle theta, and you know the distance between the planet Earth and the sun, using some trigonometry, you can calculate the distance of the object. The problem is, when the objects are very far away, that angle becomes very, very small and very difficult to measure. So you're limited to about 100 light years of distance using stellar parallax. Boy, wouldn't it be great if we had a technique that could measure objects further than that. And one of the key people who helped develop this technique was a woman named Harriet Swan Leavitt. Okay. She was born in Massachusetts. She received a bachelor's degree from Harvard University Society for Collegiate Instruction for Women. Right, this is where women were trained separate from men's now. Radcliffe. And she goes to work for the director of the Harvard Observatory, his name was Edward Pickering. And she works as a calculator. A calculator in those days was a person who would take the photographic plates that were received from the Boynton Observatory in Peru and measure the position of stars and planets on the photographic plate and record it. Okay? It was a very clerical administrative job. But she was much brighter than that. Okay? It turns out that she, along with a whole cadre of women, about 20 to 30 women, were employed as calculators. Pickering hired men to do it first, and he found that they were too sloppy. And so he hired women to do it, and Harriet was one of his premier calculators. And she measured and cataloged photographic plates from the Boynton station. And she was assigned to look for something called variable stars. And the photographs were in a region of space called the Small and Large Magellanic Cloud. And she found over 1,700 variable stars. A variable star is a star whose brightness varies with time. And she found something very curious. One subset of stars had a very curious light curve. A light curve is where you plot the brightness of the star as a function of time. And she noted that the light curve had a characteristic shape. It was kind of a sawtooth, shark fin shape to it. Okay? And that these stars had a period. And she noticed that if she plotted the period of the stars as a function of their magnitude, and the upper curve is the maximum brightness and the lower curve is the minimum brightness, it formed a straight line. Why is that important? Well, it turns out, and she talks about this in her 1912 paper, that if you know that you have a variable star and you measure its period, you can get its absolute brightness. So here's how it works. You have two stars, X and Y. They're pulsing at the same rate, which means, according to Leavitt's diagram, that they have the same absolute brightness, which means that if they're at the same distance from each other, they're going to have the same brightness. But when you observe them, star Y is not as bright as star X. So what you can do is you can use that equation that Kepler developed, right, the inverse square law, to calculate the distance to star Y. So all you need now is the distance to one of these variable stars, which are called Cepheid variables. If you knew the distance to one of these Cepheid variables and you found a Cepheid variable elsewhere, you could calculate how far that Cepheid variable is from the Milky Way. Problem is, nobody knew nobody knew the distance of any particular Cepheid until a Danish astronomer named Enyar Hertzsprung took up the case. So he worked in Germany. He's known for many things. He's known for stellar classification method characterizing stellar evolution. There's a famous diagram called the Hertzsprung-Russell diagram that talks about stellar evolution. It's not germane for our discussion here, but what he does is in 1913, he determines the distance to several Cepheid variables, making Leavitt's law practical. Now we have a way of measuring the distance to distant objects if we can find a Cepheid variable in that object. So what do we have? We've got improvements in spectroscopy and demonstration of nebular motion by redshift by Keeler and Slipher. And we've got a method for measuring distance using Cepheid variables with the help of Hertzsprung's data and Leavitt's law. By the way, Henrietta Swan Leavitt was nominated for Nobel Prize for her work in identifying Cepheid variables. Sadly, she had died 3 years before the nomination, and so the Nobel Prize only is awarded to people that are living. She never received it. But it tells you how important her work was that she was nominated for Nobel Prize. One last person before we get to the denouement of the story. George Ellery Hale, probably one of the most important figures in astronomy in the early 1900s. He founded the Mount Wilson Observatory in Pasadena. While there, he developed a 60-inch reflecting telescope. The mirror itself weighed almost 2,000 pounds. That telescope was commissioned in December of 1908. A little later on, getting more funding, he develops the 100-inch reflecting telescope. It's got a 9,000-pound mirror. I was just up in Mount Wilson Observatory about a month and a half ago and actually saw this telescope. It's a remarkable piece of technology for that period in time. And he championed the building of the 200-inch reflector telescope, which is now on Mount Palomar. The next Midwesterner is named Harlow Shapley. Shapley is born in Missouri. He works at the age of 16. He starts working at a local newspaper. He's a crime reporter. He decides he's going to go for his journalism degree at the University of Missouri. And so he joins the university, but he finds out that the school that was supposed to open has been delayed a year. So now he's got to figure out what he's going to study. He looks through the catalog. He sees archaeology. He says, I can't pronounce that, so I'm not going to study it. The next thing on the list was astronomy. He says, I'm going to go for astronomy. So he studies astronomy, becomes a very important astronomer in this story. So he goes to Princeton University for his graduate degree and then moves to the Mount Wilson Observatory, just in time for the completion of the 60-inch reflecting telescope. And he starts studying stars in the Milky Way. And he determines that the solar system is not at the center of the Milky Way. It's about 28,000 light years from the center. And he also estimates the diameter of the Milky Way to be about 300 light years across. Now, with some changes to some modifications to the Leavitt's law, turns out that the Milky Way is about 100,000 light years across. But now we have a way of really determining, first, where we are in the Milky Way, and second, how big the Milky Way is. The question, though, is that all there is? And so in 1920, there was a debate. It was basically they called it a debate. It was really two sides presenting their positions about the size of the universe. And Harlow Shapley was one of the debaters. And the other was Heber Curtis from the Lick Observatory from San Jose. And Shapley argued that, hey, people are seeing these nebula, but all of these nebula, they're contained within the Milky Way, and the Milky Way is the entire universe. And Curtis argued that, no, the nebula are not inside the Milky Way, they're far outside the Milky Way. And at the end of this quote-unquote debate, they took a vote, and the people that believed Harlow was right continued to believe that Harlow was right, the people that believed that Curtis was right continued to believe that Curtis was right. And so, although it was a debate, there was never any conclusive evidence as to whether the Milky Way is the entire universe or not, until Edwin Hubble. So Hubble was born, again, in the Midwest, in Missouri. He attends the University of Chicago. He studies primarily law, but he also studies mathematics, astronomy, and philosophy. He wins a Rhodes Scholarship to Oxford University, and he studies law because his father wants him to study law, although his heart was not really in it. And in 1913, his father dies. He returns to the US, and he decides, I'm not going to practice law. He teaches school for a year, and then he enters the University of Chicago and goes for a PhD in astronomy. And he completes his degree in 1917. Well, his PhD thesis was pretty well received. George Ellery Hale hears about him. He says, hey, why don't you come work for me at the Mount Wilson Observatory? But the US had declared war on Germany, and so he felt his duty to go serve his country, and he ends up being stationed in England, teaching soldiers how to use the stars to navigate. After the war, he comes back, goes to the Mount Wilson Observatory, and decides he's going to focus the now commissioned 100-inch telescope on Andromeda. And because he's got this very powerful telescope with a silvered mirror, which is capturing huge amounts of light, he's able to make excellent images of the Andromeda Galaxy, and for the first time sees elements within the gas cloud in Andromeda. And he starts trying to identify them. And he says, well, this one is a nova, and this one is a nova, and he finds 3 nova. And then he goes back into the photographic archive, and he says, wait a minute, one of those is not as bright as it used to be. And he realizes that it's a variable star. And he goes back into the archive and looks at his photos and realizes that it's a Cepheid variable. And now we've got a Cepheid variable in a nebula, which we didn't have before. So he goes and he calculates how far that nebula is. And he calculates that the Andromeda Nebula is 900,000 light years from the Milky Way. Well, Shapley had already said it's only about 300,000 light years across, so how can this be 900,000 light years away? Well, it must be outside the Milky Way. And when Shapley saw this, he basically said to his administrative assistant, he said, he just killed my universe. So in January of 1925, so in January of 2025, we'll celebrate the 100th year anniversary of Hubble's first paper, where he says, look, we've got Cepheid variables in nebula outside the Milky Way, and the universe is much bigger than we thought. But he wasn't done. Now, since then, since Hubble's calculation, Leavitt's law has been modified. It turns out that the Andromeda Galaxy is about 2.5 million light years away, but it's even further away than we thought, which means the universe is even bigger. But he continues to find Cepheid variables in other nebulae. And using the technique of Slipher, he starts calculating how fast these nebulae are moving away. And he determines their velocity, and then develops and publishes in 1929 his famous paper that shows that the velocity of a nebula is related to how far the nebula is away from the Milky Way, how far it is away from us. Okay? And there's a linear relationship between the velocity and the distance, and many people call it the Hubble constant, but I was talking to Neil as we entered, and people are trying to change the name of it because other people had proposed that there may be a linear relationship between velocity and distance. But whatever it's called, it's a very important constant, because the inverse of that constant is an estimate of the age of the universe. And right now we estimate the age of the universe to be somewhere around 13.5 to 14 billion years. But to tell you how important his data are, the left diagram is Hubble's 1929 paper. The right diagram is data from the Hubble Space Telescope, compiled in 1999. And the highlighted region is the region of Hubble's data from the 1929 paper, and the data points on the right-hand graph are from the Hubble Space Telescope. And you can see that that linear relationship that Hubble discovered in 1929 seems to hold, although the value of the slope of that curve, which is the Hubble constant, seems to be varying. But what this tells us is that a lot of things are moving away from the Milky Way. And many people interpret that as being the expansion of the universe. And I'm not going to be standing here telling you whether that's true or not. I'm not a cosmologist. We've got solar system ambassadors in the audience that can talk to this better than me. But I'll just share with you the words that Hubble used in a paper in 1931. He said, "The writers are constrained to describe the apparent velocity displacement relationships without venturing on the interpretation of their cosmological significance." So I present this data to you with that thought in mind, that I don't know what the cosmological significance of this is, but it is significant in terms of astrophysics. So what do we have? 2,300 years, people were thinking that the Earth was the center of everything, the center of the solar system, the center of the Milky Way. Those 3 decades, between 1900 and 1930, radically changed our understanding of the universe. We got a better understanding of the structure and size of the Milky Way, better understanding of the enormous size of the galaxy, and an understanding of the motion of galactic objects. And all of that is built on a legacy of science and technology that was developed from the previous 2 centuries, right? And so, Isaac Newton said, "The reason I see farther is because I stand on the shoulder of giants." And I think it's pretty fair to say that Shapley and Hubble did the same. Thank you very much. And this is a photograph of the Mount Wilson Observatory, and if you get a chance to go, I highly recommend it. It's only about 2 hours away, and the tour that I took, we actually saw the very thick piece of reflective glass, and there's a whole story about how this one was developed. It's very interesting. We can talk about that later. All right, open to any questions. Good, no question. Okay, I either bored you or thrilled you. Jim, hi. Is there any end to space? Oh boy, now you're getting into the cosmology.
Well, I know it's pretty weird question, but it seems the more we get better at being able to look out, it appears the skins don't get it.
Neil is going to answer that question. So let me just repeat the question for those who didn't hear it. The question is there an end to space? Because the more we look out, the further we can see.
So there are 2 theories of how
Neil, do you want the microphone? Bring it over.
Here, I'll hand it to him.
That was a great presentation. I think we all agree. That was excellent, Maud. There are 2 theories as to the shape of the universe. One is 2 applicable theories. There's a third, but that's been excluded. One is that it's basically flat, a flat universe. But that means that basically anything that are parallel lines in it eventually meet back at the beginning. So that still says there's nothing more than what's in the universe. The other is that basically the universe is sort of like a ball or bubble or however you want to put it, even if it's expanding. And again, everything is sort of contained within it. So the question is we now know that the universe itself, because it's 13.8 billion years old, but because of the expansion of the universe, it's believed to be about 45 billion light years across. So we're constantly learning more, seeing more things, and learning more things, but it's all things that are contained within the universe.
Thank you. And the only thing I would add, thank you, Neil, for that. The only thing I would add is that there's a limit to how much we could see, right? Beyond that limit, we can't see anything because the object that created whatever it was has moved away faster than the light is making its way to us. So, or we have to wait a much longer time, right? Yeah. Yeah, Roger.
You know, it's really all very interesting, but I'm just really interested. How does Santa Claus get across?
So, have you ever watched Star Trek? He must have warp drive on his sleigh, you know? I mean, maybe that's why Rudolph's nose is red. I don't know. Yes.
We've been talking about optical astronomy. Has there been any impact of radio astronomy?
Yeah. So after this period, they moved away. Not moved away. They expanded the spectrum that they could see, and they started using other parts of the spectrum. And you know, the Hubble Space Telescope (JWST) have detectors for infrared, near infrared, UV. And each one of those has advantages of what you can see and what you can't see. And then of course you put these things in space where you don't have to worry about interference with the Earth's atmosphere. Boy, you've got a real boom for data. And you know, maybe the solar system ambassadors know, but I'm sure that there are hundreds of satellites that have been put up to actually measure different aspects of the universe. Okay.